Hi everyone. So today's lesson is kind of wedged in between the two parts of the fundamental theorem of calculus because we want to just really practice with this idea of interpreting these functions. So we learned with the first part of the fundamental theorem that we can write functions as integrals. And so now we want to talk about those functions and talk about what those integrals tell us about a function. So this first example is really kind of going back to some older stuff. I mean, it's great to review, but also really these interpretation questions down here are probably the most important thing here. So let's see if we remember how to find a midpoint Riemann sum. Notice that this is only asking us to go from 10 to 70, so we're kind of leaving these two things out. Now would be a great time for you to pause the video and see if you can get this on your own. So to do a midpoint Riemann sum, my intervals need to include a midpoint, so I need to jump over this middle number. So here's one interval. My next interval would go from 30 to 50, and notice 40 is halfway between 30 and 50. And then my next one would go from 50 to 70, with 60 being halfway in between. Okay, so my integral here is the integral of the v of t function, dt, because t is my independent variable, going from 10 to 70. And we are approximating that using a midpoint Riemann sum. Okay, so pay attention to all my notation there. And so I'm building rectangles here. The base of my rectangle is going to be the width along the x-axis. So from 10 to 30, that's a width of 20. And then the height would be based on where this midpoint is, so that would be by 22. Plus, from 30 to 50 is also a width of 20. And then with a height of 35. Plus, and then this last one, again, another width of 20. So I actually could have just multiplied by 20 one time at the beginning, but with a height of 44. Now, I just thought to myself a second ago that I wasn't going to need a calculator, and look at me now. Let's find this real quick. So I'm actually going to do 22 plus 35 plus 44. So I added these three numbers together, and then just took that whole thing and multiplied by 20, and I got 2020. Okay. So remember, the purpose of that was to find this integral, and the integral represents the area under the curve. Okay. Oh, and I just realized this said write your answer using integral notation. So that's what I just did. This was integral notation. Okay. This is the big thing I want to talk about, is let's interpret this answer. What is this 2020? So now we've talked a little bit more using that fundamental theorem about the idea that an integral is really undoing the derivative. So if this is a velocity measured in feet per second, then this represents the feet function or the position function. I want to be careful about that though, because it doesn't mean that the position is 2020. It means the position changed by 2020. This is really like a displacement. Okay. So in the context of the problem, what I just found is that from t equals 10 to t equals 70, and this is seconds, right? Seconds. The position of whatever the object was increased, which means if it was moving left to right, it would be moving to the right by 2020 feet. Okay, so it's the change in the position. We are going to eventually talk about how could we get that actual position function. We couldn't do it with something like this where we just have a bunch of data points, but if we had an equation to work with, we'll be able to do a process to actually find the position function. Okay, but this represents the change in the position because the position is the velocity is the derivative of position. Okay, let's move on to the stuff that I think is actually more important today. Okay. So we've seen questions like this before, right? Here's a function. Look at all the questions that I'm asking you. I'm asking you about critical points, asking you about inflection points, all these things you've seen before, right? But I want you to notice how this information is phrased. This is all asking you about the g function, and this graph is the f function, and this represents the relationship between f and g. Basically, g is the integral of the f function. G is the integral of this graph. So when I start a question like this, and you're going to see me do this lots of times, I kind of write out a key for myself. I would write, for example, here that G represents the area, because G is an integral, right? So if it's asking me about G, which I don't see a question where it specifically asks for a G value, but it's telling me to find the area. So now let's talk about what G prime would do. If you took the derivative of this, think about what we just learned. The derivative of the integral would just bring you straight down to the f of x function, which is the graph itself. So when I ask you about G prime, you're reading values straight off the graph. Okay, so then what does G double prime represent? Because that question is going to come up here too. Well, that's the derivative of G prime, which means it's the derivative of f, so it's f prime. So if you were looking at the graph of f and I ask you about f prime, what is it that you're measuring, or what is it that you're reading about f? That would be the slope. So I always set these three things up for myself so that later in the problem, when I'm being asked all of these questions, I can keep straight which thing am I looking at. Am I looking at an area? Am I looking at a slope? Am I looking at the graph itself? Okay? So let's see. The first question says find G prime of 3. Okay, so reading up here, G prime is really f. So this is the same thing as just saying what is f of negative 3. And that's just the graph. And I sort of wrote over it. But f of negative 3, let's talk about this point right here, would just be 2, because I'm just reading it straight off the graph. Okay, G double prime of positive 3, so that's talking about this point right here. Well, G double prime is f prime, which is the slope of the graph. So I need the slope of this segment right here. And let's see, this looks like it's going down 2 and over 2. So my slope, let's see, I'm going to write this, f prime of 3, which would be negative 2 over positive 2, otherwise known as negative 1. So I just did rise over run there. Okay, here's where the real fun begins, and this takes us back to stuff that we talked about before. When is g of x increasing? Okay, so without looking at any of this stuff, anytime I ask you this question, when is a function increasing, I hope your brain is going here and saying, what I really need to know is when is g prime positive? Okay, well, we said g prime is really f, right? So I need to know when is f positive. I'm just talking about when is this graph above the x-axis. So that would be from negative 4, so here, all the way over, all of this is positive, to that positive 3. Just making sure my number is right. 1, 2, 3. Yep. From negative 4 to positive 3. Now, this question didn't specifically say that I had to justify, but you know that we love our justifications with questions like this. This is essentially what we want to say, but we also need to include this information, that g prime is really f. Okay. Now, with a free response question, as long as you say that once, you're covered. So if you had this written on your paper someplace as part of your response, you wouldn't have to restate it. But just to be safe, here's what I'm going to say. Negative 4 to 3, because g prime, which is really f, is positive. Okay, so I know that for G to be increasing, I need G prime to be positive. If we're talking about F, though, we need to make sure we make this connection between G prime and F. Okay, so we're saying G prime is the same as F and F is positive. Okay, critical points. Critical points of G would be when G prime is equal to 0, right? So again, G prime is really F. So we're going to say this happens here at -4, happens here at +1, and then happens again here at +3. And again, our reasoning would look very much the same way. G prime, which is really F, equals 0. And again, if you had already written this somewhere else, you could get away without saying it again here, but we're going to practice that a lot. Okay. So for inflection points, maybe this is a good place to point this out, that remember up here when we made this connection that G prime is really F? So if this is the graph of F, that's essentially the same as me telling you this is the graph of G prime. And by making that change, I've basically turned this into a problem from like chapter 5, right? Because back in that chapter when we were first doing all these questions like this, that's what I was giving you, was a derivative of a function and asking you all of these things. Now I'm just defining the function as an integral of another function, okay? But it's the same thing. So tell me, where do inflection points come from when you're looking at the graph of a derivative? Because that's essentially what you're looking at here, okay? This would be when G prime changes direction, right? Because that indicates a change in concavity. So we're changing direction. Let's see, I'm trying to keep this on the screen here for you. But I'm seeing a change in direction here, right, at this point up here, because I went from increasing to decreasing. Now, here looks like it could be, but it didn't actually change from decrease to increase. This one did, though. And then we went back to increasing, and then here we changed again. So it's every place we change direction. That would be at x equals -3, x equals 1. So I do want to point out this point right here is both a critical point and an inflection point. That's totally possible. And x equals 2. And remember, for this justification, I would probably say something more specific than changes direction. I would say changes from increasing to decreasing or decreasing to increasing. Okay. This is the exact same picture. I just put it here so I didn't have to keep, sliding it back and forth. So when do we have a local minimum? Okay, so anytime I'm asking you about a local minimum, first we need a critical point. So we need G prime to equal 0, and we need it to be changing from negative to positive, right? Because then it's going from the original function, the the G function, would be going from decreasing to increasing. So again, this graph that I'm looking at is G prime. So here are my critical points, right? Here, here, here. I'm looking for one specifically where that derivative changes from negative to positive. That's happening right here. Here we are positive to positive, so this one actually isn't a maximum or a minimum, right? And this one goes positive to negative, so that would represent a maximum. So my answer to this question would be x equals -4. This one does ask for a justification. So I'm going to say because G prime, which is F, changes from negative to positive. On the AP test, I think I would take the time to write those words out. For the sake of your notes, that should be okay. Okay, G of x concave down. Now, remember, concavity actually has to do with the second derivative, but since we're looking at G prime, we want to try to talk about it in terms of what G prime is doing. So to be concave down, what you really want is for G prime to be decreasing. because that's when the slope would be negative, right? And the slope really represents that second derivative. So where are we decreasing? Let's see, we're increasing. And then we said this was a change in direction. So now from here to here, we're decreasing. So that is from -3 to +1. And then we increase again for a little bit, and then we're decreasing until the end. So that is from 2 to 4. And I would say, because that is when G prime, also known as F, is decreasing. I do see some students talk about this having a negative slope. You're not wrong if you say that, okay? You're right that it is a negative slope. The thing I worry about with using that terminology, with saying negative slope, is it's too easy to mix it up with just being negative. So like, for example, up here when we talked about this being increasing, it's because the function was positive. That's different than having a positive slope, right? You can be positive, and that doesn't necessarily mean your slope is positive. So that's why I like to use the increasing, decreasing terminology, because it's not as easy to mix up. Okay, write an equation for the tangent line to g of x at x equals 0. Okay, so here is the tricky thing about this. Remember that for a tangent line, the first thing we need is a point. So I need to know what the y value is that goes with 0, right? I need g of 0. Okay, we haven't done one of these yet with this question, but remember up here we said anytime I'm talking about just the regular g function, I'm really talking about an area. If you notice how this is defined, this is talking about an integral from -3 up to whatever our x value is. So to find this g of 0, what I will need is an integral from -3 to 0 of this f function, which means I'm finding an area, right? So, okay, -3 is this pink dot right here. So this is where I'm starting, and I'm going to 0, so this is where I'm ending. So I need the area of this shape in here. And let's see, that doesn't make a real nice shape. I might split it. I think I'm going to split it right here and make a triangle, and then this would be a trapezoid because you've got those two parallel sides there. Okay, so I'm going to say for the triangle, it's 1/2 times 1 times 2. And then the trapezoid would be 1/2. The height of the trapezoid would be here, so that looks like 3. And then my bases would be the two vertical sides, so that's a 2 and a 1. Okay, so that is a 1, 1/2 times 1 times 2. This is 3 times 3, so that's 9/2. Okay, well, this 1 can really be a 2/2. So 2/2 plus 9/2 is 11/2. So that's my coordinate, right? 11/2. Now the good news is that took a little bit of work, right? To get the point, the slope should be easier. Because for the slope, what I really need is what is g prime of 0, right? That's my derivative, so that's going to give me my slope. Okay, if we look at what we set up here, g prime is really just f. So g prime of 0 is really just saying what is f of 0. F of 0 would be 1, right? This point right here, f of 0 is 1. So that means g prime of 0 is 1. And so here's my point, here's my slope. So my tangent line is going to look like this. Y minus my y coordinate of 11/2 equals my slope of 1, and then x minus the x coordinate of my point, which is 0. So this actually would clean up really nicely. You don't have to clean it up if you don't want, but that 1 and that 0 make a lot of things go away, and we would just have x plus 11/2. That's your tangent line. So you want to get really good at being able to jump back and forth between these three things. And that's why I find it easiest to just write that down first before I start one of these graph problems. But really, this should have felt very similar to when we did this back in like Unit 5. Okay, when we were doing all these things, it's called graph analysis. We are doing graph analysis again, except we are defining the function using integral notation and then talking about how, okay, well, the derivative of that integral is just the graph itself. So you're really looking at a derivative graph here. Okay, on this next page, and I'm going to leave you to pause the video here for a second. This next page is a table for you to fill in. Again, where you've got this function defined as an integral, and all of these things should look like things we've talked about before, right? So we want to talk about the relationship between g and f and when do all of these things occur. So instead of talking through all of them, what I'm going to do is I'm going to just post this page with all of these filled in, but I would actually recommend that you try to fill these in yourself and then check them with mine, okay? So I'll have that posted. I will also start the second part of this lesson video with just this page, and I'll give you an opportunity if you want to just pause it and copy it there, okay? All right, hopefully that helps. We've got one more example to go.